Hello, welcome to Basic Differentiation Rules and Rates of Change. My name's Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is a Math 1411 Calculus at UTEP. Chapter 2, Differentiation, corresponds with Larson's 11th edition of the Calculus text. Section 2.2, Basic Differentiation Rules and Rates of Change. First of all, the derivative rules, part 1. The derivative of a constant function is 0. That is, if c is a real number, then the derivative with respect to x of a constant is 0. But think about it, what is a constant function? A constant function is a horizontal line. And what is a derivative? A derivative is a slope of a tangent line. So if I have a linear function, what's its slope? Its slope is 0. The derivative is the slope. The slope of a constant function is 0. Power rule. If n is a rational number, then the function f of x equal x to the n is differentiable, meaning the derivative exists, and the derivative of x to the n, where x is our variable, is equal to n times x to the n minus 1. So we bring down the exponent and we subtract 1 to get the new exponent. Don't forget the x. A lot of people forget to write the x. For f to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. So if we have a negative exponent, we have to be careful. It might not be differentiable at 0. So find the slope of the tangent line at the given value. If f of x equals x to the fifth and an x value of 2, the slope of the tangent line is the value of the derivative. Using the rules, we know that the derivative of x to the fifth is 5x to the 5 minus 1, which we simplify to be 5x to the fourth. That's our derivative function. That's so much better than the limit derivatives using the difference quotient. So the derivative at 2 is 5 times 2 to the fourth. Order of operations says 2 to the fourth is 16. 5 times 16 is 80. It's a pretty steep line for a tangent line. If f of x equals x to the 2/3 at an x value of 1, using the power rule, we bring down the 2/3. We'll have x to the power of 2/3 minus 1. That's 2/3 x to the negative 1/3. And you can rewrite it with a positive exponent as 2 over 3 x to the 1/3. Evaluating when x equals 1, the slope is the value of the derivative at 1. When I substitute 1 for x, I'll have 2 over 3 times 1 to the 3rd power. But 1 to the 3rd power is 1. 1 times 3 is 3, so that's just a slope of 2/3. Notice, this is a fine derivative. 2/3 x to the negative 1/3, that's a great derivative. But if I'm going to evaluate it, I'm going to write it with a positive exponent first, so that it's easier to evaluate later. Example 3, 1 over x to the 3rd at x value of negative 2. F of x equals 1 over x to the 3rd is a fine function, but writing it with a negative exponent, x to the negative 3, allows us to use the derivative rules. So the derivative, we bring down the negative 3, x, negative 3 minus 1, right? We subtract 1 from the exponent, gives us negative 3 x to the negative 4. Make sure you do that subtraction correctly. Once we go to evaluate it, we'll take negative 3 x to the negative 4 and rewrite f prime of x equals negative 3 over x to the positive 4. And then we can evaluate the derivative at negative 2. Negative 3 over negative 2 all to the 4th power is negative 3/16. Some more rules. The constant multiple rule says if f is a differentiable function and c is any real number, then c times f is also differentiable, so the derivative exists. And just like with taking the c, the constant, out in front of a limit, we can take the constant in front of the derivative. So the derivative of a constant times a function is the constant times the derivative of the function. Similarly, the sum and difference rules tell us the derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives. Since the derivative is defined by limits, the same rules that applied to limits are going to apply to derivatives. So let's find some quick examples here. If f of x is 3x to the 5th, then the derivative, we leave the 3 alone, that's our constant. Find the derivative of x to the 5th, so that's 5x to the 5 minus 1, also known as that 3 still. 5x to the 4th power. 3 times 5 makes 15, x to the 4th power. And for right now, maybe you need to write this first step. Maybe you're already prepared to go on to the second step. But eventually, meaning in about a week, I would love it if you could be at this step. You can look at 3x to the 5th, multiply to get the 15, x, subtract 1 from the exponent to the 4th, so you don't have to write the steps in between. Since we're just learning it now, I'm still going to write those steps. F of x equals 17x squared. We're going to leave the 17 alone. When I take the derivative of x squared, I bring down the 2, x to the 2 minus 1. That's 17 times 2x to the 1st power. 17 times 2 is 34, and we rarely write a 1 as an exponent. It's kind of an understood, so we'll call that 34x. Don't forget we could have negative values. If f of x equals negative 5x to the negative 7, my negative 5, my coefficient, is a constant. I leave it there. I take the derivative of x to the negative 7 by bringing down the negative 7. X to the power of negative 7 minus 1. That's negative 5, parentheses. Negative 7 times x to the negative 8. Negative 5 times negative 7 is 35. X to the negative 8. In general, for the derivative, the exponent goes down 1 when we're taking a derivative. But remember, with negative numbers, it makes it look bigger. But it's negative, so it's actually smaller. Fact. With constants, constant multiples, and sums or differences, we can now find the derivative of any polynomial or root function using rules rather than limits. Do you remember finding the derivative of root functions using the limits? We had to rationalize and do this and do that, and it was so algebraically heavy. Now we don't have to do that. So let's use the rules of differentiation to find the derivatives. If f of x equals 9, remember, a constant function has slope 0. Derivative is 0. If f of x is the 4th root of x, we'll first rewrite it, x to the 1/4 power. Then we'll take the derivative, 1/4 x to the 1/4 minus 1, which is 1/4 x to the negative 3/4. And then we will rewrite. Right? It started as a root function. Let's finish it as a root function. The 1's in the numerator, the 4 is in the denominator. The negative in the exponent says take it to the denominator. X to the 3/4, that's x to the 3rd, and then the 4th root. The denominator is always the index of the root. F of x equals x squared minus 2x plus 3. I'll take the derivative of x squared and get 2x to the 2 minus 1. Leave the minus sign. The derivative of 2x, I'll leave 2 alone. The derivative of x, right, that's x to the 1st, so that's bring down the 1, x to the 1 minus 1. The derivative of 3, that's a constant. Right? Derivative of a constant is 0. What is this? This is 2x minus 2. Keep in mind that x to the 0 equals 1 as long as x itself is not 0. So anytime we get to a 0 power, we'll end up with just a constant term in our derivative. When y equals 8 minus x cubed, the derivative of the constant 8 is 0, minus the derivative of x cubed is 3x to the 3 minus 1, so that'll give us negative 3x squared. Keep in mind there's a difference between a constant and a coefficient. So in number 3, 3 is a constant. The derivative of a constant is 0. But negative 2 is a coefficient. It's in front of the x, so we treat it differently. Example 5. If f of x equals 2x cubed minus x squared plus 3x, our derivative, 2x cubed, we leave the coefficient 2 alone. Finding the derivative of x to the 3rd, we'll have 3x to the 3 minus 1. We'll simplify that in a minute. Subtraction. The derivative of x squared is 2x to the 2 minus 1, plus the derivative of 3x, I'll leave the 3 alone. For x, I'll bring down the 1, x to the 1 minus 1. 2 times 3 is 6, x. 3 minus 1 gives us squared. Minus sign, 2x to the 1st power. And here, remember 1 minus 1 is 0, and x to the 0 is 1. So we'll just have the constant 3. Don't go too far. Don't then just say, oh, that's 0. No, you've already found the derivative. That's the result. Notice that the derivative of any term involving mx, anything that looks linear, the slope is always just going to be the coefficient m. Right? So the slope of a linear equation or a linear term is always the coefficient of x. And it's because this part is linear and we know the linear slope is the coefficient of x. Part 3 of our rules, we could take a look at two basic trig functions. The graph of the sine of x, right? Sine is this nice little S-curve here. And if I were to estimate the slope at 0, at pi over 2, at pi, at 3 pi over 2, and at 2 pi, I would find that I get exactly the values that are the graph of cosine. And so this is one way, graphically, of showing that the derivative of sine of x is cosine of x. And we could do a similar type of drawing for the derivative of cosine of x, which is the negative sine of x. Negative sine of x. So let's use some rules of differentiation to find the derivative. The derivative of g of t equal pi cosine of t. Remember, pi is just a coefficient. It comes out in front. The derivative of cosine is negative sine of t. So my derivative is negative pi sine of t. The derivative of y equals 7 plus sine of x. The derivative of 7 is 0. The derivative of sine of x is cosine of x. So the derivative of sine of x plus 7 is just cosine of x. If y equals 5 over 2x all to the third power plus 2 cosine of x, the first thing I'm going to do is rewrite. 2 to the third power is 8. X to the third power in my denominator. Still have my 5 in the numerator and 2 cosine of x following. But let's rewrite that. Instead of x to the third in the denominator, let's call that 5/8 x to the negative 3 plus 2 cosine of x. Because now when I find the derivative, I leave my coefficient 5/8 alone. X to the negative 3, I bring down the negative 3, leave the x, subtract 1, plus 2, coefficient. Derivative of cosine is negative sine of x. And we multiply. 5/8 times a negative 3 is negative 15/8 x to the negative 4 minus 2 sine of x. And I can go back to the form we had before with positive exponents. Negative 15 over 8x to the 4th minus 2 sine of x. Now, find the slope of the graph of the function at the given point. Find the slope of the graph at the given point. So this says, without saying so directly, evaluate the derivative. The slope is going to be the value of the derivative of the tangent line. Slope of the graph, I mentioned in a previous lecture that's also the slope of the tangent line of the graph. And it tells me where to evaluate it here at the point 2, 2. So 8 divided by x squared, we're going to rewrite as f of x equals 8x to the negative 2. Find the derivative, leave the coefficient 8 alone. Bring down the negative 2x, subtract 1 from the exponent. When I multiply, I'll have negative 16x to the negative 3. I'm going to rewrite that with positive exponents so that I can evaluate. So f prime of 2 is negative 16 over 2 to the third power. Negative 16 over 8 is negative 2. Again, find the slope of the graph. F of t is 3 minus 3 over 5t at the point 3/5, comma 2. We'll rewrite it. Instead of 3 over 5t, the t is going to come up with a negative 1 power. 3/5 is now my coefficient. The derivative of 3 is 0. Subtraction. 3/5, the coefficient stays. The derivative of t to the negative 1 is negative 1. T to the negative 1 minus 1. 0. All right. The negative 1 and the negative 3/5 makes a positive 3/5. T to the negative 2. I'm going to rewrite that with the t to the positive 2 in my denominator so that I can evaluate. Substituting 3/5 in for t. First I square 9/25. 9/25 times 5 will be 9/5. Instead of dividing by a fraction, I can multiply by its reciprocal. This is 15/9, which simplifies to be 5/3. If f of theta equals 4 sine theta minus theta at the point 0, 0, the slope of the graph at that point, the derivative of 4 sine theta is 4 times cosine theta minus theta. Okay, now remember theta, this is a linear term. There's no exponent on the variable at all. So the derivative of a linear term is just going to be its coefficient. So that's a minus 1. Evaluating at 0. f prime of 0 is 4 times cosine of 0 minus 1. Cosine of 0 is 1. 4 minus 1 is 3. Finding the derivative. We will have rules for this later on, quotient and product rules and other ways of dealing with more complicated functions, but for now we don't have any of that. So we simplify by dividing. Remember, writing as a common denominator is one thing, but we can also rewrite it so that each of the terms in the numerator has that denominator, right? Going backwards on adding fractions with the same denominator. So this is x to the third over x squared minus 6 over x squared. Simplify. X to the third over x squared is x minus, instead of 6 over x squared, I'm going to call that 6x to the negative 2 so I can use my power rule. The derivative of x is 1, right? Linear term. Derivative is just a coefficient, minus 6. My coefficient stays out in front. Bring down the negative 2, x to the negative 2 minus 1. This will give us 1 plus 12, x to the negative 3. And I'll rewrite it as 1 plus 12 over x cubed. We don't have a product rule yet either, so the first thing I'm going to do is I'm going to distribute. So 3x times 6x is 18x squared. 3x times a negative 5x squared is a negative 15x to the third. My derivative, I'll leave my coefficient 18 alone. The derivative of x squared is 2x to the 2 minus 1. Subtract, leave my coefficient of 15 alone. The derivative of x cubed is 3x to the 3 minus 1. When I simplify, 18 times 2 is 36. X to the 2 minus 1, that's x to the first power. Minus 45, x squared. Let's make this more challenging. A cube root, right, is the 1/3 power. So a cube root in the denominator, if I wanted to rewrite it, would be a negative 1/3 power. So 2 over the cube root of x is 2x to the negative 1/3 plus 3 cosine of x. 2 is a coefficient, stays there. Bring down the exponent of 1/3, x to the negative 1/3 minus 1, plus 3, the coefficient we leave alone. The derivative of cosine is negative sine of x. Multiply, 2 times a negative 1/3 is a negative 2/3. Negative 1/3 and a negative 1 makes negative 4/3, minus 3 sine of x. And then I rewrote it as y prime equals negative 2 over 3x to the 4/3, making a positive exponent, minus 3 sine of x. I didn't put this back in root notation, as maybe I should have, but roots and rational exponents, very similar. One is not necessarily any better than the other. All right. Let's determine the point or points at which the graph of f of x equals x plus sine of x in one interval from 0 to 2 pi has a horizontal tangent line. So let's break it down. Horizontal lines have 0 slope. So we're looking for points on the graph, right? Determine the points, looking for points on the graph where the derivative is equal to 0. First thing we're going to do is find the derivative. Derivative of x is 1, plus the derivative of sine of x is cosine of x. We need to solve when is the derivative equal to 0. That's when 0 equals 1 plus cosine of x. Subtracting 1, negative 1 equals cosine of x, and on this particular interval, that only happens one time, at x equals pi. But pi is not a point. We want to find the point xy, where x is equal to pi. So we go back to the original, right? The derivative told us where to look, but the original function tells us what it is. So when x is equal to pi, y value, f of pi, is pi plus the sine of pi. And we know that the sine of pi is 0, so this just has an outcome of pi. Our answer is that the given function, f of x equals x plus sine of x, has a horizontal tangent line at the point pi comma pi. Okay, what do these derivatives really mean? Here's an example. The number of gallons N of regular unleaded gasoline sold by a gasoline station at a price of P dollars per gallon is given by N equals f of P. So the number of gallons is a function of the price. So what does it mean to have f prime of 2.979? Well, the derivative, it's a slope. It has units of n divided by units of p. So f prime of 2.979 is the rate of change of the number of gallons sold divided by price per gallon when the price is $2.97 per gallon. Whew. Is this derivative usually positive or negative? Usually this value is negative as stations will sell less fuel at higher prices. We've seen high prices for so long, though, it's hard to say. Thanks to Math is Fun for the graph of the constant function. I didn't use Desmos this time, but I always love Desmos.com for my graphing calculator needs.